Shall I start now? Can you hear?
Yes, sir, we are live.
We'll start, right? Okay.
Yes.
All right. All right. Good afternoon, and good afternoon all. And many thanks for coming out for this live session. And in this next 1 hour, I would like to review the important points of um, important points of the module 7 that deals with the quantum dot. Okay, so what we will do is we will try to run through the basic physics of quantum dots and single electron charging phenomena, single electron transistors, shell filling, and introduction to artificial atoms. And the detailed physics of all this will be there in the recorded lecture in the all the three in split into three different lectures. All right. So when we say quantum dots, these quantum dots are man-made droplets of charges. Those are small conducting regions contain, containing few to a few thousands of electrons. They are connected to the rest of the world through weak links. We can think they are connected to the rest of the world through some kind of tunnel barrier. Okay, and the size of these quantum dots could be anywhere from a few nanometers to a couple of micrometers. And I also want to make the distinction right here that quite often quantum dots or nanoparticles were kind of used in synonymously, but they are not. That is not true. Nanoparticles are nanometer-sized grains or particles which does not need to be conducting, whereas quantum and it does not need to show any quantum mechanical effects either. But the quantum dots doesn't need to be nanometer scale. Those are quasi zero-dimensional structures with exhibiting quantum mechanical effects of electrons or transport. Okay, so these are a few different ways to realize the quantum dots. There is this epitaxial re-release quantum dots where you have a substrate and you deposit small regions of another material which are small in size using machines such as molecular beam epitaxy machines. And the second kind here shown here, these are self-assembled structures. That means you start from the using the bottom-up method, and you have conducting small regions. And the third and fourth here, those are released on large material by limiting the mobility or motion of the electrons. And in this case, in the first case here, there are, you have what we have here is etched regions which containing uh, which is confining the electrons. So these are the quantum dots here. Okay, and the small neck-shaped regions, you can think those are the weak links to connect to the source and drain and between each quantum dot. And the last case here, what you have is you have surface gates, Schottky gates on the surface of two-dimensional electron gas, which we have went through in detail in a couple of few previous modules back, where you use voltages to confine electrons, and what you get eventually is you will get small conducting regions here, and this region you can think of as source, this region you can think of as a drain, and electron can go from the source to drain through this small confined region. Okay, and when you apply voltages onto all these gates, what you are going to make is you make a small constriction here, another constriction here, and these constriction will serve the purpose of tunnel barrier. The good part of these two designs are As you can see, there are also small regions here which are conducting. You can apply voltages to these regions. These are called gates, and control the electrostatics and control the size of the common dot, control the number of electrons and all these details. So these are completely controllable quantum dots. As of these are basically pretty much the size is uncontrollable. What I meant to say is you cannot change the potential electron number, you cannot change size, you don't have much freedom. But in these two cases, you have a lot of freedom to control the electrostatics, control the energy scales, and control the dynamics of electrons by applying voltages. So these are voltage tunable quantum dot, and for the rest of the lecture, we will confine mostly to these two designs. Okay. All right. Now, let's look at the transport through this quantum dot. So, let's consider what is the basic mechanism of transport. In this first case, what I have is a resistor, which is a macroscopic object. Okay. So this is like size of like a few millimeter, and you'll have a large capacitance associated with that. So the process of transport involves adding an electron and removing an electron, adding an electron from the source side and removing an electron from the device to the drain. So the transport is a sequence of these two processes, which I have represented here. You have a small region in case of a corner dot, or you have a large object in case of a classical device such as a resistor, and you have an electron jumping onto the dot from the source side and then jumping off to the drain from the dot. Okay. Now, the energy required to remove or take an electron, the electrostatic energy, is something called charging energy, which we all have learned in our 12th grade. So this electrostatic energy is generally referred to as EC. It is E square by 2 C sigma, where C sigma is the capacitance or self-capacitance or total capacitance of the object. Now, when we consider the resistor, you can run the number. So this have nanofarads of capacitor, and electronic charge, E is 10 to the power minus 19, that is the order. So when you take E square, that will be 10 to the power minus 38 divided by 10 to the power minus 9, that is for the that is the order of the capacitance. So this is a very, very small number. This is very, very small, almost equal to 0 when we consider the energy scale of the system. When I say energy scale, what that means is energy scale given by the temperature. That is the working condition. Okay. So when you consider this is a very, very small number. So the charging energy is insignificant. So at any given temperature, practically possible temperature, these electrons will shuttle back and forth through this device, and you don't require any extra effort to push these electrons on and off this device. What that means, this process is going to go on, and you will not really notice this charging energy. But now, when you have a really small object like a quantum dot, these capacitance are like in femtofarads or autofarads, and at cryogenic temperatures, you can see, we can run the number again, that you will observe this charging energy. That means you need to put an extra effort to run the electrons through this quantum dot, through this object, because naturally the energy given by the temperature is not sufficient for this transport to happen. What that means is the transport through system generally is blocked. So for example, to observe this charging energy effect, at room temperature, your quantum dot size need to be 30 nanometer. This number is calculated based on the capacitance, because size translates into capacitance, then capacitance translates into the charging energy. That's what it is. And 77 Kelvin, this will be like 50 nanometer. and for Kelvin 2 micrometers. You can see as you reduce temperature, you reduce the energy scale. What that means is against EC, the energy available for thermal energy available for transport is lower, so that you need extra effort or extra push to put the electrons through the system. That means to observe this at higher and higher object sizes, or higher and higher size, or higher and higher dimensions, you need to go to lower and lower temperature. That's what it says. Okay. So in nutshell, what we can say is to observe the quantum size effects, you need cryogenic quantum size effects or quantum confinement effects, and especially this charging energy. This is not really a quantum mechanical effect. If you think carefully, it's a completely classical effect, but the quantum part comes here only because the charge is quantized. Okay, and that has a lower limit. That is the charge of electron. So that's where the quantum mechanics comes here, but it's not really a quantum mechanical phenomena. It's a simply electrostatic or effect or electrostatic charging phenomenon. Okay, so to observe this charging energy, you need to go to cryogenic temperatures. That is the point here. Now, I should not say strictly that quantum mechanical effect does not come in picture, but there's a small catch here. The catch is, what we are looking at is you have a quantum dot with a well-defined electron number. Okay, electrons are confined inside the quantum dot. What that means is, the electron, whenever you observe it, the electrons are always there. That means the leak out time for electrons to the rest of the world through the circuit put forth by you is sufficiently long, or the electron stays pretty much almost all the time inside. This charge leak out time, or the leak out time for the electrons to the source or drain, is pretty much the RC time constant of the circuit, where R is the resistance of the tunnel junction, or resistance of the link that the quantum dot is connected to the rest of the world, and C is the capacitance, total capacitance of the quantum dot. Now, this charge leak out time is given by RC sigma tau RC, and the energy associated with this time scale is the charging energy, because whenever the charge jumps on or off the dot, the energy of the system fluctuates by EC, and your aim is to observe this fluctuation, or make sure that that fluctuation is substantial and it actually overshadows other energy scales such as temperature energy. So what that means is the energy uncertainty associated with this time scale delta E, that should be much small compared to the charging energy. Charging energy should dominate. So delta E is given by h by tau RC. That is the quantum mechanical uncertainty relation for energy and time, connecting energy and time. And the energy uncertainty, that is h by tau RC, should be far less than the charging energy, where charging energy is given by this formula. So the point here is EC should be a robust quantity compared to other energy scales in the system. So when you work out this, tau RC is RC sigma, and when you substitute for EC and tau RC and rearrange the terms, what you would get is the resistance, because this is an inequality. Okay, this is an inequality here, so that will translate to inequality here. So the resistance limit, that means there is a lower limit for the resistance to make sure that you observe that you can observe this charging phenomena or electrostatic charging phenomena of electrons through this in these devices. Okay, so that is 25.813 kilo ohm. That is just a ratio of two fundamental constants, h and then square of the charge of electron, E square. Okay, and that is 25.813 kilo ohm. And this is kind of a magical thing. Say you have not used any any sophisticated derivations or any rigorous derivations in this case. You simply applied the quantum mechanical uncertainty relation and you got a number which is equivalent to the reciprocal of the quantized conductance value or the quantum mechanical limit of the resistance. Okay, this is the same number that you have seen in quantum Hall effect or same number that you have seen in quantum point contacts. So what I'm trying to say here, this fundamental constant came out magically just from this very simple assumption of uncertain relation connecting the energy uncertainty and this classical, electrostatic charging, charging time, RC time constant. Okay, so what this says is the resistance, there is a minimum limit for resistance. If the resistance is lower than 25.813 kilo connecting the quantum dot to the source and drain, then the electron number may not be a robust number, may not be robust. What that means, the number of electron number in the quantum dot will fluctuate. What that means, charging energy is may not be well defined, or you may not be able to observe charging phenomena. So this lower limit is another factor which comes from quantum mechanical conservation. Lower limit for the tunnel junction resistances or weak link resistance comes from the quantum mechanical uncertain relation. This is exactly where the quantum mechanics comes in picture for this single electron charging phenomena. All right. Now let's look at a transport device. So the circuit represents a quantum dot which is connected to source and drain, and there is also another electrode which I have added. It's again another capacitor which is by which you can apply, okay, you can change the electrostatic energy of the quantum dot. Okay, and we just learned that in normal condition, when the temperature energy is lower, you have to push the electrons using giving an extra energy to push it on the dot and off the dot. In normal state, no transport will happen because the charging energy is substantial compared to temperature energy. So what you're going to have is, if you take an IV, current voltage characteristics of the quantum dot, I have a simple cartoon of the electrochemical potential of the dot here, where these green lines represent the electrochemical potential of the dot, and this D and S represent source and drain levels. Okay, so under normal condition, what we have is there is an extra energy that is required to put an electron, that is charging energy, that is above the source and drain. That means when you start from a zero voltage, if you try to measure the current will be zero. And as you ramp the voltage further, at some point of time, what you will reach a situation where the source is in resonance with the electrochemical potential for the n plus next electron. Okay, then the current will start rising. The same thing in the opposite direction also. Okay, so you start from zero bias, then you rise slowly, but at some point of time you will reach the voltage level which is corresponding to the electrochemical potential for the n plus 1 electron. Then the electron can jump onto the dot, then jump off the dot. Again, remember, here also only one electron can tunnel at a time, because the energy required for tunneling two electrons is twice the charging energy. That much you have not supplied. You have supplied only just enough energy to have one electron go through it, and one. So that is E by C sigma in voltage scale, or E square by C sigma. Okay. Now, when you supply E square by C sigma, you can have one electron going on through the dot. Okay, and so the transport phenomena is basically single electron oscillations. That means you have one electron on the dot, then you can put the next electron only after you remove that electron from the dot. So it's always electron by electron. Okay, only one electron can go at a time. So that is why this is called single electron transport regime. And this device is also called single electron transistor. Why this is called a single electron transistor? We will come to in a minute. Okay. So here in this specific situation, the transport through the corner dot is blocked. That corresponds to this window near the zero bias. So this is blocked because the classical electrostatics or Coulomb repulsion of the electrons which are already there on the dot. If you look at the physics of charging energy, you can realize that it is because of the Coulomb repulsion of the electrons which are already on the dot. Okay, so the transport is blocked because of Coulomb repulsion. So this regime is generally referred to as Coulomb blockaded regime, or this phenomena of transport shutdown to the dot is generally called Coulomb blockade. Okay, and the moment you lift the Coulomb blockade, the electron through the dot goes one by one, and in that case the charge state of the dot fluctuates between n and n plus 1, given n is your starting state. Okay, there's a charge state fluctuation by one electron when the transport happens, and this was first observed in 1998 in this landmark paper. What they had is they had a lot of grains of tin which is deposited onto a substrate, and they try to measure the transport, vertical transport through this, because that involves pumping electrons from the top to bottom through these small grains. And what they found is the IV characteristic, the conductivity showed a behavior which is shown here. This is nothing but a derivative of this one, okay, what you are seeing here. So this is a DC current, this is an AC current. This you can see is dV by di. Okay. So this is how the resistance actually behave. This is pretty much nothing but if you look carefully, this is a derivative of this current. And you can also see that the effect is more and more prominent when you reduce the temperature. 1.6 Kelvin has the best behaving, and as you increase temperature, this peak is getting smoother and smoother and smoother, and around 80 Kelvin is almost gone. So that is when the temperature energy overtake the charging energy. Okay, and then the charge state is no more well defined on the dot. Okay, so that is the summary on the transport. Now let's look at the electrostatics. The total energy of the dot has two parts. Number one, it is the energy because of the voltages, gate voltages on the dot, that is CGVG. By then CG, this also has the dimension of charge, CGVG. Then you also have a discrete part. This is the continuous part, because the gate voltage that you are going to vary, that's electrostatic potential that you are changing by applying the gate voltage, and that is a continuous variable, whereas Ne, that is the number of electrons on the dot, that is a discrete variable. Okay, so the total effective charge on dot is actually CGVG minus Ne. That's what it is. Okay, and square of that divided by the capacitance will give you the electrostatic energy of the dot. Now if we plot this one, this is nothing but it's a parabolic plot. That's what you are going to get. Okay, as a function of the voltage offset by Ne. Okay, n can vary from 0, 1, 2, 3 like that. So you will get parabolas corresponding to every number of n. Okay, so that whenever these two parabola meet, nearby parabola meet for n and n plus 1, that is when the energies corresponding to n and n plus 1 are same. Okay, that is the place where the transport can happen. So whenever the gate voltage CGVG satisfies E dot n is equal to E dot n plus 1, that is here, that gate voltage will give you a current to the dot. Otherwise, it is blocked. What that means is, if I draw here, in this regime, in this regime, or here, the electron number inside dot cannot change much. It is fixed. The electron number can change only when the energy corresponding to this parabola, that is n plus 1 parabola, and energy corresponding to n parabola are same. They are degenerate. That is called a charge degeneracy point. At that point, the electron number can oscillate between n and n plus 1, and that is the condition for single electron transport. Okay, so when I vary the gate voltage, what I am going to get is, at some gate voltage, I'll have this degeneracy condition between n and n plus 1, then I'll get the current can flow through this. That is this condition. So if I have the electrochemical potential levels of the dot aligned this way, then the transport can happen even at a very, very low voltage. In the previous slide, what we looked is the transport takes place only when you increase the bias to certain level, which actually compensates for the charging energy. But here, what we are saying is, instead of that, you can bring the energy level down in the window, source and drain, which is much smaller than charging energy. What you are doing there is, you are making these two charge states degenerate by changing the electrostatic potential of the dot, and you will reach this condition, and you can have these two charge states degenerate n and n plus 1 at this stage. Similarly, if you go further, the next level you can pull in, go further, next level you can pull in, and you can pull all these electrochemical potential levels sequentially by varying or by sweeping the gate voltage, which is connected to the dot. Okay, so in this case here, at all these places, the electrochemical potential of the dot is not favorable for transport. The electron number is fixed, and no current flows through that correspond to these regions. And whenever these two parabola meet, you can have transport, and you will get peaks in the current. Okay, so these correspond to stable charge state here, and here the charge state is unstable or it fluctuates. So when you sweep the gate voltage and measure the current through the dot, you will get a series of peaks. Those peaks are called Coulomb blockade oscillation, and this is a representative data from one of the device. What you are doing here is, you are making the gate voltage negative, and you get a series of peaks, and there are more details to it, why this peak height reduces as you reduce the voltage, and why the period is changing. Those are final details which I will not address right now, but we can always discuss that later, or maybe after the lecture. So, but the point here is, you get a series of peaks as we reduce the gate voltage, and these peaks are called Coulomb blockade oscillations. Okay, and this is a landmark phenomena. It's a touchstone phenomena of transport through the quantum dot. And the green line here represent the overall charge of the dot. So whenever you pass one Coulomb blockade peak, you increase or decrease, depending upon which direction you are going to pass. You increase or decrease the overall charge on the dot. So for example, you charge from n, then n plus 1, n plus 2, n plus 3, and so on. Okay, that is how you change the overall total number of electrons on the dot. What you're doing is, you can think of like you're pulling the levels. It looks like a ladder, and you're pulling the level down, and as you pull each level below the drain, that electron is locked inside. Then the next one comes. If you pull further, that goes below the drain, that electron is also locked, so that you are increasing the number of electrons as you go up in the gate voltage, or you're decreasing the number as you go down in the gate voltage. Now you can naturally think that if you rise it further and further, you will reach a point when you have no more levels left, and you can empty the dot, and there are no electrons in that region. That is also possible, and that is exactly the regime where you work when you keep this dot as qubits, quantum dot qubits, where you want to go that last electron and store information on the quantum degrees of freedom of that electron. That is the regime that you are going to work when you use these quantum dots as qubits. Now, let's look at the IV characteristics of this dot a little bit further. So, what you have is, let us consider the situation where we are not really worried about the gate voltage now. There are only source and drain. So, as I told, these levels here represent the electrochemical potential of the dot. Okay, and of course, these are not only two levels. There are further levels upwards, which I can draw. So there are levels up further. Okay. Normally, the transport is shut down. If you want to get a transport, you have to raise the source or drain, source to drain voltage, drain to source voltage. Okay, so you have transport blocked in this region, and when you increase this VDS, the drain source voltage further, you will basically raise this level, and you will be able to access the next available electrochemical potential level. Okay, and but now instead of making this source drain voltage high, what you can also do is you can bring that level down, as we have just explained the previous slide, into the window of source and drain. In that case, what you can do is you can get the transport, get the level within the window, and you don't have to go that high in the source voltage to get the transport through the dot. That means you will have a shorter or a narrower blockade regime, and then you can get transport in a lower source drain bias. If you go further, you reduce the source drain voltage further, but you can pull this level in resonance with both of the levels. Then you can get literally and practically you can get transport even when the level is in resonance with the source and drain when zero source drain voltage is applied. What that means is when you change the gate voltage, you can reduce the source drain bias window for the transport to happen. So this Coulomb blockade region will get narrower and narrower and narrower and narrower, and finally it will merge. So you can visualize a situation where you have a really large window and really large source drain window for the transport to happen, and within the center region that is represented here. Okay, there is no transport happen here. Okay, now when you increase the source drain bias further, then you can get current increasing in both direction. Now, when you change the gate voltage, you can narrow that window down. You can further narrow the window down. Finally, the window will be, you can make sure that the source drain window at zero itself, you can get the transport. So, usually these quantum dot measurements are done with a combination of both source and drain voltages, okay, varying. So in one axis, what you do is you vary the source drain voltage, other axis you vary the gate voltage. Okay. In this specific case, is a cartoon. I will show you the real data very soon. You have the gate voltage varying in the vertical direction and the source drain in the horizontal direction. And in this region, which is kind of diamond-looking region, you have no transport. Okay, no transport happens. That you can convince from this level diagram here, from this states here. So what happens is here, as I marked, if I go to this specific gate voltage and this specific bias window, you will that I have marked as the blue curve here. You have blockaded region in the middle. Then when you go further, you get transport through. That's what we discussed the previous. Now, when you vary the gate voltage further, make it lower, then this source drain bias window becomes narrower. Okay, and finally that will be zero. So what you are getting is you are getting a diamond shaped region of no conduction, as soon as you are out of the diamond, that diamond shaped region is when you do a two-dimensional plot where one axis is a color plot, it's actually three-dimensional plot. The third dimension here is the third axis here is the color. Okay, so the black color or dark color here means no current flowing through, and once you are out of that region, then current will rise. Okay, so you have one axis is the source drain bias and other axis is the gate voltage. Okay, and when you do such a plot, what you are going to get, you will get diamond shaped regions of no current flowing through, and this is called Coulomb diamond. And this is a must data that you one need to show to say for sure that you have a quant dot. Okay, and these Coulomb blockade oscillations correspond to this tip of this diamond. Okay, and as you increase the bias, you have actually, if you do it in the middle, you get a very sharp Coulomb blockade oscillation. But if you increase the bias further, then current will stay on for this window, and that is means the Coulomb blockade peak will get broader and broader and broader. And this is a very important plot as far as quantum dot measurements are concerned, because you can get a lot of information of the geometry of the dot. It's kind of interesting because just by measuring currents and current versus voltage, you can calculate the capacitance, you can calculate the size of the dot. Okay, quite often say shape of the dot also you can do that, because this vertical distance or the gap where the current is 0 is going to give you the gate capacitance. This horizontal distance where the current is 0, that's going to give you the charging energy. The gate capacitance is directly related to the gate voltage. You get the gate voltage period between the Coulomb blockade oscillation, this period. Okay, that's what this is. Okay, so this period is this period here. Okay, so that period delta Vg, the voltage window, that is going to give you the gate capacitance, and this source and bias voltage window is going to give you total capacitance. Okay, so total capacitance is directly related to the size of the dot, and if you have multiple gates, then you can get the capacitance of all these gates. If you are using multiple gates to form the dot, then you can get the capacitance on each of the gate. That is basically a measure of the shape of the dot. Okay, so you can get directly both the size of the dot and the shape of the dot just by observing, but just by looking at the dimension and shape of the Coulomb diamond plot. Now, these are some practical Coulomb diamond plots. In this specific case, what we have is you have some small grains of aluminum trapped in the middle. You can think of some small grain is here. So you have source and you have drain region. Okay, let me change the color here a little bit. This is source region and this is the drain region, and you can have some small grains of aluminum. Sorry, small grain of gold. Okay, trapped here. So when you measure transport through the system as a function of gate voltage and also source drain bias voltage, as we just discussed, we are seeing diamond shaped regions. These are the diamond shaped regions. Okay, this is what we just discussed. But these are diamond shaped regions. Okay, and also I want to emphasize this point here, that whatever the level diagrams that we have drawn so far, those are not the quantum mechanical single particle levels. Okay, so those are the electrochemical potential levels of the dot as a function of gate voltage. So though, let me go back here. Yeah, these levels, what I have drawn here, these are not single particle levels, because we have not started defining the quantum mechanical behavior of electron except that the charge is quantized. Okay, so these are electrochemical potential of the dot which you can change by varying the gate voltage. These are not the single particle levels or single particle states of the electron confined in the dot. That we will discuss very soon. Okay, so what I am trying to say here is the number of states available inside a dot is kind of infinity, because if you take a metallic dot, you know that the single particle levels are, because there are so many electrons in the system, it's a metal, the electron concentration is so high and the levels are so close. Okay, so these levels inside dot is kind of continuous, what as shown here. So what you have is you get a small gap in energy. That's a gap because of the charging energy, that is this number here, just at the Fermi level. That's all. Okay. So you need to, what this means is you need to beat this charging energy to put an electron and take an electron from the dot. That's it. That is that gap. So that means you are going to, you can add almost like infinite number of electrons. You can never empty the dot completely, because you have that many states inside the dot. Okay, that is this state. That is the case with metallic quantum dots. Okay, and what that means is you will get infinite number of Coulomb diamonds and you will get infinite number of Coulomb bracket oscillations. Okay, so this will continue forever in both directions in this case. Okay, now here in this specific example, what they have done is they have a device which basically it's a gold quantum dot. They have fabricated by electron migration. So because of electron migration, you get a small, it's almost like a constriction where one grain of this gold is trapped in between, which is connected to source and drain. And getting this also kind of luck. It's not that you don't know how much control. It's just a demonstration purpose. Okay. As far as the real device is concerned for quantum information processing, this is not a choice. This is only to demonstrate this phenomena. Okay. And it's one of the earlier paper. So you have a small quantum dot, a grain of conducting region, which is trapped between the source and drain. That is made by electron migration. Now, the controllable structures are the gated semiconductor quantum dots. So here what you have is you have a two-dimensional electron system as we discussed before, and you use gates to control the tunnel barrier, gates to control the dot. In this case, what you have is you have a conducting region here, which is defined by the H. Okay, the dimensions are here. This is probably like 200 to 300, maybe 200 to 250 nanometer wide. Then these bright regions are gates. When you apply negative voltage, you are going to create a confinement. Okay, so you will have electrons all over this region. The moment you apply negative voltage to these two gates, what you are going to have is you are going to have a tunnel barrier. So you have one tunnel barrier here, another tunnel barrier here, and you have a small quantum well, which is roughly parabolic shaped. Okay, and that is your quantum dot. And just by varying the voltage, you can actually change the size of the dot and also the tunnel rate through the system, because tunnel rate depends upon tunnel barrier height and width, which you can change by changing the voltage. And this is a Coulomb diamond plot from such a device. Now, what you can see here is, unlike the previous case where the Coulomb diamond plots are almost similar in size, which does, you have infinite number of Coulomb diamonds. In this case, what you are seeing is you start with a very small Coulomb diamond, and as you reduce the gate voltage, you can see that these Coulomb diamonds start increasing in size, and finally you have nothing. Almost it doesn't continue, stops at some point of time. So Coulomb diamond closure, the absence of a Coulomb diamond closure is basically saying that you don't have any more electrons left in the road, because you don't have any more transport happening through it. That means you don't have any more electrons left in the road. This is basically your when you go negative in the gate voltage, that is this horizontal axis here, you are pushing the levels up like that, and eventually all the levels are done. You have no more electrons left in the dot. Okay, then you say that your dot is empty. But now you might ask why the size of this diamond change, because remember the size of the diamond is basically a measure of the total capacitance, which is a measure of the total size of the dot. The capacitance goes inversely with the size of the dot. So when you reduce the voltage, what you're doing is you're making the size of the dot smaller and smaller and smaller. That means your size of the Coulomb diamond will increase. Okay, and eventually you will empty all the dot. So the increase in the size of the dot is saying that you are reducing the size of the dot. Increase the size of the diamond is saying you that you are reducing the size of the dot. Okay, so this is another device with a similar geometry. Okay, here also you can see the same phenomena where you start with a very small diamond size and you increase the size of the diamond as you make the gate voltage, as you reduce the gate voltage. Okay, what that means is you are reducing the size of the dot, that is reflected as the increase in the size of the diamond, or the Coulomb. When I say diamond, it's a Coulomb diamond. Okay, so and finally you don't have any anymore. You don't have the closure of the diamond, probably somewhere here. Then after that nothing happens. Okay, so what that means, you have emptied the dot. All right, and let us look into the semiconductor dot a little bit more carefully. So far what we have discussed is the states inside dots are the states or electrochemical states which are defined by the electrochemical potential of the dot. And you have a continuum of states inside the dot. These are filled, these are empty, and all you do is when you vary the gate voltage, you will add one more electron here. Okay, that's what it is, and the overall energy is given by this expression that involves only electrostatic energy. But when you reduce the size of the dot, what you would do is you also will start seeing the electrostatic, now in addition to the electrostatic energy, you also will start seeing the single particle energy differences too, because this Coulomb blockade oscillation is periodic for a large dot or a metallic dot, because you have infinite number of states and it's a continuum of states. Okay, so only we need to worry about the electrostatic energy. But the moment that dots is very small, the energy difference between the n+1 and n electron configuration, that also involves a single particle term, delta, I would say delta En. Normally you see EC, that is the electrostatic energy difference between the n+1 and nth state, nth configuration for a large dot. But when you have a smaller dot, also the single particle level will come into picture. Then remember, the Coulomb blockade oscillation period is a measure of the charging energy. Okay, so when you do a large quantum dot, you get a periodic array of Coulomb blockade peaks, just like here. But the moment you have a smaller dot where the delta En also is comparable, or that also starts playing the role, then the spacing between these peaks also will reflect that contribution, the single particle level contribution. Let's consider this specific case. This is a toy model, but we can have situations very close to this. Okay, in this case, let's consider that the levels are equally spaced. And when I say levels here, they are single particle levels. Earlier, you had a continuum of states in this region, in this energy window, but now this continuum of states have been split into single particle levels. Okay, and as per the electron filling, each state can take 2 electrons. Okay, now when you vary the gate voltage, you will pull one of these levels into the window, then you will get a peak in the current in the Coulomb block oscillation. But when you vary the electrostatic energy further, you have one more state left, actually, single particle state left there. Okay, that is spin up and spin down states. So that state will be available now. But now the next state is actually EC plus, that is charging energy, plus delta E. Now you have to go to the next single particle level. So the periodicity of Coulomb blockade oscillation is going to change, and that is going to reflect the single particle state. That will tell you what is the size of the dot, what is the shape of the potential, what is the size of the potential, and all the other details. Okay. So naturally, in this specific periodicity, the levels are equally spaced. You can tell that it actually corresponds to parabolic confinement. Okay, that is where you have equally spaced levels available in the potential. Well, whereas if you had some other kind of confinement, say this is a toy model, this generally it doesn't happen at all, a square well, then this has a different periodicity. According to that periodicity, the delta En will vary. Delta En is the energy separation between the adjacent single particle states. That delta En will vary. So you will not get this kind of, here it's actually doubly periodic. This is a doubly periodic structure, that is for a parabolic well. But you will not see this for a square well. You will see some other filling. Okay, some other series of, or some other periodicity. So just by looking at the periodicity, you can tell what is the confinement, what kind of confinement you have. Okay, so now this is the case when you have smaller dots. Okay, so what you are talking here is, you are talking about the filling sequence or shell filling in this structure. This is very similar to how you fill electrons in a quantum dot, in a natural atom. So if you consider a circular disc-shaped atom, that is what you generally get. You can approximate the naturally gate-defined quantum dots to disc-shaped quantum dot. They are also called pancake kind of quantum dots. Okay, you can solve the potential and you can solve the wave function, and those are actually called Folk-Darwin states. It's a two-dimensional parabolic confinement, which looks like this. These are called Folk-Darwin states, and these are the wave function. And this shell filling or degeneracy of these Folk-Darwin states are given here. This is a textbook problem. Okay, so the first orbital can take 2 electrons, second can take 4, third can take 6, fourth can take 8. What that means is, the shell filling will happen in this periodicity for a disc-shaped atom. What that means, the Coulomb blockade period is basically a shell filling, right? Because when you are past one peak, you are filling 1 electron. The period of the Coulomb blockade oscillation will tell you what is the energy sequence or how the shells are filled. Okay, so if you look at that, this is a disc-shaped quantum dot. You can refer the paper for more details, or also the recorded lecture. And what you're saying is, the period is kind of, initially it might look random, but it's actually not random. Okay, and the size of the Coulomb diamond, and also the size of the Coulomb diamond also look random, but it's actually not random, because that has to tell you the sequence of filling, because that is telling you what is the energy, how much energy you had applied every time to fill the next electron. That is going to tell you where are the levels. Okay, so in this case, the 2 electrons filled, third one you have applied larger energy. Again 4 filled, then the 2 plus 4, 6, 7th will have larger, and so on. So you get this larger gap, 2, 6, 12, and so on. And that is exactly what happens when you have Folk-Darwin states. Okay, and you can, what you're seeing here is your shelf in just like a natural atom, you are filling electrons in a quantum dot. So that is why these quantum dots are also called artificial atoms, because depending upon the outer shell configuration, the properties of this quantum dot will be different, will change. Because when you go from left to right in a periodic table, the properties are changing because you are changing the size, you are changing the shell, outer shell configuration. I mean, in when you say, when I say in a nutshell, okay, there are details to it, but that is not the point. The point is the reason why you are having different properties for different elements is because it's shell filling, it's electronic configuration, because all these are made of electrons, protons, and neutrons, all the material, right? The reason why gold has its own color is because of its electronic configuration. Okay, so in this case, that is for a three-dimensional confinement. Atom, natural atom is a three-dimensionally confined structure. So you can have similarly an artificially two-dimensionally confined structure. This is a artificial two-dimensional atom. So you can also envision a periodic table for this kind of filling too. Okay, so let me stop at this point here and maybe take some questions if there are. So these quantum dots are also called artificial atoms, and and they can also have, depending upon the electronic configuration, they can also exhibit different electrical and electronic properties. Now we can take some questions if there are any. Yeah, I can see there is. I'm looking at one of the questions. It's a very interesting question. So, thanks for this question. So, Coulomb blockade is applicable for any kind of charge transfer, but usually, of course, I mean, you also need to have a system to confine this. It is just an electrostatic effect, and it's an electrostatic effect plus uh, you also have the condensation of the charge. Okay, so usually Coulomb blockade is observed for electrons and holes, very routine. Both you can observe, but those are the only reports that I'm aware of. But in principle, it doesn't have. It's not a quantum mechanical effect. It's a classical effect. So these large quantum dots are generally called classical dots also, and these, if you can confine some other particle and you can have the transport defined by this mechanism, then you can observe it in any system. There's nothing which is forbidding you from not observing it. It's just a charging energy. It actually originates from the charging energy concept or electrostatic charging concept. And you can also ask any questions in the previous modules that you have attended, which if you need a detailed answer, that we can always discuss in person too. Okay.
Hello, sir.
Yes, please.
We'll end the section, sir.
Yeah, okay, fine. You can stop it, right? Okay, thank you.
Yes, sir.
Thank you.